First of all, thank you to ESIC for giving us an opportunity to present at this workshop. I'm delighted to be here, both with this group, which is at the forefront of energy transition. And frankly, because it's an in-person event, I can see some faces. So you have noticed from the agenda, this is the panel focusing on Australia. And I have three of my colleagues dialing from Australia. So let me take an opportunity to introduce them. First, Chris Davies, who is a manager of future energy systems, and his team's primary focus at present is developing the engineering framework, which is a toolkit to define full range of operational, technical, and engineering requirements to prepare for a range of operating conditions, including 100% renewable penetration into the grid. The next presenter would be James Lindley, who is a group manager of system capability division within operations. And his team oversees a program to manage the technological transformation of power system of the NEM, including re-establishing primary frequency control, use of wide area electromagnetic transient modeling to assess power system security, and operational management of DER. His team is also responsible for ancillary services procurement in the NEM, including system restart. And we got a Sam Christie, who is she's manager of network planning, and Sam's team is responsible for assessing system strength, inertia, and other system security needs in national electricity market, as well as supporting other long-term network planning activities. Although before our presenting here, we would like to fully acknowledge number of teams involved in this work, number of engineers who put together a number of hours in developing this work, which we are presenting at this stage. So as you would notice, this is the Australian panel. So let me tell you a bit about Australia. Those who have never traveled to Australia or traveled many, many years ago, Australia is big. Okay? It's a continent, it's a country, and it's an island. On the left, which is on screen, it's where say with Australia. Yeah, Nick, you got it?
It's an attitude.
Yeah. Okay, geographically, okay, so one just to make a bit of a with some so how really take okay. Right, so this is where I'm trying to compare Australian power system with some of the other power system of the world where we have seen large penetration of inverter-based resources. Australian system, which would mainly be speaking, is the eastern system, covering 5 states: Queensland, New South Wales, Victoria, South Australia, and Tasmania. Okay. And it's a long, skinny network compared to traditionally found interconnected system across the world. There are several takeoff points where we have seen a large penetration of inverter-based resources, and they are far from the backbone transmission network and the key synchronous generation center. So what's happening in Australia? Okay. This is the outlook from the 2020 integrated system plan, draft integrated system plan. There are a number of scenarios, you can look at it. Our most credible scenario is a step change scenario, which is on the purple. What we are seeing that about 14 gigawatt of coal generation is going to retire by 2030. And all coal generation capacity is likely to close by 2040. This is the economic modeling. And if the hydrogen superpower takes off, then the modeling shows that 20 gigawatt out of 23 gigawatt currently installed capacity is going to retire by 2030. And since the publication of this report, which was December last year, the largest coal power station in Australia decided to close down by 2025. It's only 2.5 years from now. And that's a 2.8 gigawatt coal power station. So to give you a bit of context, the Australian system is 35 gigawatt peak system, very smaller than you would find in American context. So this was about the generation, what's happening on the demand side. This is one of my favorite slides. The one on the left shows the forecast demand. It's shrinking, it's going down, okay? Going down at a rapid rate. The last time when I checked, the peak demand record was earlier this year only for one region out of 5. And previously, it was, before that, it was 2011. So it's almost 10 years ago. And when I look at minimum record, we are regularly hitting minimum demand record in Australia. The figure on the right is only for one region, which is South Australia, where we had a record minimum demand of 104 megawatt. Now, when I say demand, I'm talking about the operational demand to be fed from transmission connected generation. 104 megawatt on 21st of November last year. And you can see it's largely driven by the rooftop distributed PV generation. This South Australia is a gigawatt scale system on an average. Right? On average, its demand is gigawatt. On that day, it was only 100 megawatt. So like how I was talking about 40 to 70, 50 to 70% of DER penetration, currently South Australia has so much of DER that it can supply its whole region solely by distributed PV. Moving on, the next slide. This is the, again, a draft integrated system plan. You can notice on the bottom side, the black coal and brown coal is retiring, it's shrinking. It's the rate at is going to retire is faster. And the outlook is dominated by transmission connected wind, solar, and distributed PV, which is the millions of individual solar rooftop panels. And the picture I'm painting could be similar for other countries, right? But the rate at which the change we are seeing is phenomenal. And to be honest, it's really scary. So combining all together, what we have seen is on the left-hand side of the figure, where you can see the renewable penetration in the grid. This is the real-time data on 30-minute average on the left-hand side. For the last 3 years, it is increasing at 10% every year. Right side is the forecast. Okay? What it is showing us that by 2025, we would have enough renewable potential that the entire grid can be fed by 100% renewable generation by 2025, 2.5 years from now. And so our target system, as the topic of this workshop, is collaborating with our stakeholders to develop an energy system that is capable of handling 100% instantaneous renewable penetration by 2025. So the outcome, like retirement of a retirement of a coal plant, increase in the grid scale wind and solar, distributed PV, batteries, syncons, they're all encouraging. And we are actively collaborating with the leading international organizations to facilitate this energy transition. So with that background, I would like to hand it over to our first panelist, who will take us through a deep dive of what we have planned for it. Yeah. So Chris, over to you. Do you want to share your screen?
I will. Thanks, Nilesh.
Okay. Good.
Just tell me when you can see this.
Yep, we've got you, Chris.
Yes, good.
Thank you.
Thank you, and good afternoon, everyone. Big thanks to ESIG for the invitation to come and speak today. I'd like to begin today by acknowledging the traditional owners of the lands on which James, Sam, and I are presenting on, paying our respects to their elders past, present, and emerging. For me in Adelaide, South Australia, this is the Kaurna people of the Adelaide Plains. My presentation today gives an overview of how we're bringing some structure to what is often an overwhelmingly complex problem space. As Nilesh explained, Australia is seeing its power systems transition at an incredibly rapid pace. The trajectory that we're on as a country is towards a low emissions economy. And a key enabler in achieving this is going to be a low emissions power system, and also one that increasingly carries more and more load as we electrify other emission intensive sectors like transport and domestic heating. A low emissions power system for us is one that's regularly operating with very high levels of renewable generation, particularly variable inverter-based sources like wind and solar PV. In our view, one of the biggest engineering milestones on the path to a low emissions power system will be successfully operating the entire power system for the first time at 100% instantaneous penetrations of renewables. So that's the first half-hour period where all our generation is coming from renewable sources. If we can prepare for this first occurrence, our view is that we'll be well on our way.
Chris, I'm sorry to interrupt. We're still on the first slide.
Yep.
Your opening
that's right.
slide. Okay, just making sure. Yep. I'm sorry.
No, that's good. Thanks, Ron. Our view is that we'll be well on our way to operating with high levels of renewable generation on a regular basis. As Nilesh noted, our forecasts indicate that as soon as 2025, we could start to see periods where there's enough renewable generation potential to meet all customer demand. And being ready to manage 100% instantaneous penetrations of renewables by 2025 is a hugely ambitious goal. But the reality is, this is the future that's rapidly approaching, and we need to get ready for it as quickly as we can to ensure we're able to deliver the most efficient outcomes for consumers. These periods of very high renewable resource potential are forecast to get increasingly more frequent every year from 2025. And every step that we take to confidently operate at high penetrations of renewables needs to be celebrated as a success. But how do we begin to approach such a challenge? For us, this led to the development of the engineering framework. The framework provides a series of structures to help break down the complexity. It helps us systematically work through sort of what needs to be done, and provides a toolkit to help enable a collaborative industry approach by providing a common map and language to inform discussions. To begin with, we considered the problem in three main parts. Firstly, where are we starting from? We weren't starting our transition flat-footed. There's a huge amount of work happening across industry already. And the first step was really to take stock, which is the left-hand side of this image. Second, where do we want to get to? We needed to define the endpoints that we wanted to prepare for, and that's the right-hand side here. And thirdly, what are the gaps that need to be bridged to get us from where we are to our desired futures? And that's the middle of this diagram. Within this overarching sequence then, there are a number of important structures that we developed. We defined firstly a series of focus areas and groupings to help segment our thinking about different dimensions of designing, planning and operating the power system. And that's the circle here on the left, which outlines 10 focus areas that we landed on, grouped into three broad areas. So fundamental power system attributes and what we need to do to maintain those with a different generation mix. The requirements for an operable system to make sure that we can actually make use of those attributes. And then a number of technology integration questions, particularly for distributed energy resources, which is really, it's a totally new field of focus compared to the past. We used these focus areas initially to help map the work already underway across industry. Moving to the right-hand side then, if we think about where we want to get to, we distilled the plausible futures, different plausible futures into 6 defining operational conditions. And these were 6 conditions that each drive some change in thinking or approach to planning and operating a traditional power system. They're all expected to occur under all our forecasting scenarios. It's just that the timing of when they arise will be different between different scenarios. But timing aside, it was clear that we need to be ready for each of these end states at some point, and therefore they provide a sort of a no regrets guidepost for what are we preparing for. Those 6 conditions. So the first one, fewer synchronous generators online. I mean, I think this is the core of the transition challenge in my mind. It's how do we prepare to run a system without the big spinning machines that it was built around in the first place? Ubiquitous rooftop solar. So for us, this is being able to operate for periods where, as Nilesh noted, at times, most of the generation in particular regions is coming from behind the meter consumer grade solar PV. The third one is extensive grid scale variable renewable energy. So other times of the day where all of our generation is coming from large scale renewables distributed across the country. The fourth is structural demand shifts, and this is really thinking about what changes when we start to couple other sectors to the electricity system, significantly increase our demand, add in new industries like hydrogen production industries. Fifth, responsive demand. So starting to think about how things change when we get a more active demand side. And the last one is widespread energy storage. And here we're thinking about what needs to change in our thinking when we've got a lot of energy limited plant operating in our system. While many of these are interrelated, they each pose some unique questions for consideration. And preparing for the first periods of 100% instantaneous penetrations of renewables will particularly mean preparing for the first three operational conditions, with some consideration for the other three as well. Through the third step in this process, which is the gap analysis process in the middle, we were then able to overlay both these structures, the focus areas on the left and the operational conditions on the right, as frames of reference to help unpack as comprehensive a list of potential gaps as we could. At each stage in this initial process, we've worked closely with stakeholders to test and challenge our thinking, and also to tap the collective knowledge base. I can't understate how important collaboration is to navigating the transformation of the power system. We need the collective ideas, skills and horsepower of the whole industry to successfully navigate this transition. But that said, given the breadth of material that we've necessarily had to cover, it's been a real challenge to get the right balance between meaningful and effective engagement and timely progress. I'd also note that there's no perfect taxonomy for this sort of process. I think that's okay. What we have here works, and all of the problems and all the gaps have got a home. And I think it's an important takeaway more broadly that we need to get comfortable with imperfections if we want to make progress. We could have spent years just debating an optimal taxonomy, and meanwhile, the changes in our power system would be overtaking us without us having effective preparations in place. So that process led us to the initial roadmap report, which we published in December last year. And this unpacked the spectrum of potential gaps that we need to consider in order to prepare for those 6 operational conditions. Again, this was a process of determining a taxonomy and a structure that would make the breadth of detail digestible. In the end, we identified over 300 potential gaps, but in the end, we're able to distill that back to a 3-page summary, sort of grouped according to the 3 focus areas of system attributes, system operability, and system integration. And then to give decision makers a starting point, we also distilled a series of key decisions that we felt require consideration in the next 2 years. This key decision mapping process sought to articulate the importance of considering parallel pathways in areas where there's currently too much uncertainty to determine a single preferred path just yet. And I'll take you through the key decisions pathways a bit more over the next few slides. Firstly, decisions relating to maintaining key power system attributes. And there are 2 broad considerations here. Firstly, maintaining essential power system capabilities as the synchronous generator fleet exits. That's the left-hand side. And then on the right, managing variability and uncertainty of variable renewable energy sources. Firstly, on the left, we think about sort of how do we replace the services traditionally provided by synchronous generation. There's a lot of open questions about the roles that advanced inverters can play. Given the short window of time we have to prepare for reduced synchronous generation operation and potentially early exits of coal units, we felt that the uncertainty of technology capabilities was best dealt with by pursuing parallel paths until a preferred technology path or combination of paths becomes clear. On one path, encouraging efficient opportunities to replace some of these essential services by using synchronous sources that don't produce any megawatts, so synchronous condensers particularly. And here we're thinking about maximizing opportunities to convert existing synchronous generators to include SynCon capability, and also encouraging the inclusion of SynCon capability on new synchronous generators where there's a local system need. In parallel, exploiting every opportunity we can to fast track the development and proof at scale of advanced inverter capabilities. And in that regard, I'd note our national renewable energy funding agency is running a $100 million trial at the moment to encourage 100 megawatt plus grid forming batteries around our system. And that process is in train at the moment. We also identified the need for flexibility in the delivery of essential power system services, accepting that we don't know everything today and allowing for evolution in our understanding over time. So that's creating frameworks that can easily evolve along with our learning rather than trying to hard code everything from day one. Given the time it takes for reforms to play through, how do we set up a framework that sort of gets the boundaries in place but kind of evolve with our thinking? The second broad consideration here on the right-hand side is managing variability and uncertainty of variable renewable energy. Firstly, we need to acknowledge that there are inherent limits to what's possible for operational forecasting in a high renewable future, given the inherently chaotic nature of the weather as a major fuel source. Therefore, we need to exhaust the options to improve our operational forecast, but only up until we hit up against diminishing returns. And then to support this, we need to develop regulatory frameworks that allow for efficient management of uncertainty over different timescales. So that's frameworks that allow us to operate for a plausible range of outcomes rather than operating with a single deterministic outcome in mind. Next, we have decisions relating to system operability. So this is really thinking about the tools and processes needed to help support system operation in a more complex power system. We've grouped things into two key areas here. On the left-hand side, uplifting power system modelling and analysis capability. And on the right, how we maintain an operable and resilient power system. On power system modelling and analysis, this is firstly about making data and models easier for the relevant parties to access them, which is a big barrier at the moment. Increasing the number of capable professionals across industry, and quite seriously, if anyone's looking for a move to Australia to work on some of these questions, there's a high demand across industry for power system engineers here at the moment. One action we're looking at this year is how we can simplify the migration process for skilled power system engineers from overseas. We're also looking at how do we streamline our modelling processes to speed up analysis times. And then considering how the appropriate use of engineering margins can minimise modelling requirements. So how do we avoid creating unnecessary burdens and delays due to the pursuit of unnecessarily precise answers? So looking for the right models for the right purposes and not modelling more than we need to. On the right, maintaining an operable and resilient system. So this is looking at how do we improve operational visibility through things like more high-speed data recorders, uplifting control room tools for situational awareness and proactive decision-making, establishing suitable operational margins that allow flexibility in an increasingly complex environment. So again, let's not engineer the power system onto a knife edge unnecessarily, and see if we can give ourselves the room to learn as we go in a safe way. We need to accept there's a lot we don't know. So considering how the use of engineering margins can help speed up the transition without taking on more risk than we need to. And finally, considering how we progressively build operational confidence on the live system without affecting consumer experiences. And this is the question of how do you build that operational confidence when we can't ever stop the system? How do we do it quickly? How do we do it safely? Finally, key decisions associated with integrating new technology, particularly DER, distributed energy resources. There's two broad areas here, managing periods of really high distributed PV and a number of broader technology integration questions as well. So firstly, we need to establish sufficient visibility of distributed resources, and that's particularly looking at enhanced monitoring options to give us the right level of aggregated visibility. We also need to establish effective device performance standards for distributed resources and ensure compliance with these standards. And compliance is a big pain point for us at the moment. Again, we have some parallel paths here from there. So on the top path, establishing the bare minimum requirements for security. So thinking about emergency curtailment capability of distributed resources, ensuring clear roles and responsibilities in a high distributed resource future. So how do you maintain effective under-frequency load shedding when all of your load blocks are saturated with generation? How do you maintain stable load blocks for system restart in the middle of the day when all your load is being met behind the meter? And then in parallel with that, sort of market reforms to drive more efficient outcomes sort of beyond those minimum backstop requirements. And here we're thinking about incentivizing load and storage flexibility, implementing dynamic operating envelopes to maximize the potential of distributed resources within limits of distribution networks, building scalable and secure data architecture, scalable and secure architecture for data exchange, and integrating distributed resources into energy and system services markets. Okay, hopefully you're still with me. That's a pretty whirlwind tour of the different dimensions that we feel we need to wrap our heads around to enable this transition. And these key decisions for system attributes, system operability, and system integration are where we concluded in December last year with our initial roadmap. The big question for everyone then was, how do we progress from problem definition into tangible actions? Which leads us to where we are today. Over the early part of this year, we've been working through a process of converting gaps into actions. Given the pace of transition, we felt it was important to tackle things progressively, moving quickly to identify a first tranche of no regret priorities to act on, while we continue to refine our longer term plans. To do this quickly, we started with the key decisions roadmap that I just stepped through and identified initial actions to help us take a meaningful step towards addressing each of those decision points. We then did a sweep of the full list of over 300 potential gaps to identify any additional gaps that had a really pressing system security risk or a long lead time that would need to sort of be worked through to realise a significant future system security or consumer benefit. From there, we developed a draft action list, which we tested with a select group of stakeholders. And I'm delighted to say that in about 3 hours' time, we're going to be publishing the results of this prioritisation process in our engineering framework priority actions report. This report lays out 46 priority actions that we believe need to be progressed across industry in the near term. And these include some existing actions that are already underway across industry, as well as some proposed new actions where the implementation pathways aren't yet clear. This slide highlights the 12 headline priorities that we felt were particularly important in the near term to help prepare for 100% instantaneous penetrations of renewables. So I won't go through them all, but just to pick out a few. Action 1, which involves implementing a new regulatory framework for the provision of system strength. And Sam's going to talk you through that in more detail in her presentation. Action 2, which is a program of power system studies to look at power system security at times of 100% renewable generation. I also point you to Action 9, which involves the trial of subsections of the network at 100% inverter-based operation. And both Action 2 and Action 9 are being informed by our work in the South Australian power system, and James will touch on that in his presentation next. I also think Action 3 and Action 8 might be of interest to many of you. Action 3 seeks to define the necessary power system support capabilities that we might value from grid forming inverters to help guide equipment manufacturers and developers in their decision-making processes. And I note, and to Nilesh's point, we're watching the developments in the US and Europe closely in this regard to see how we can best collaborate. Action 8, which is our work to develop and implement an integrated roadmap for our operational technology over the next 10 years. This work's well advanced. There's been a lot of sort of international discussions on this one. And the roadmap for that is due for publication this June. All right, I'm going to leave it there for today. Hopefully that's been sort of a useful overview of how we're approaching this rapid journey towards 100% instantaneous penetrations of renewables. We've got a lot more work to do from here, and we haven't got all the answers yet, but what we found is that bringing some structure to the problem space definitely makes it a less overwhelming and more manageable process. For anyone that wants to dive a bit deeper into the priorities for the year ahead, or any of the sort of the past work in this process, I'd encourage you to take a look at the report that's come out today, or will be out in a few hours. And all those reports are available on the engineering framework page of our website. So thank you again. I look forward to taking some questions later, and I'll pass you over to the capable hands of James.
Thank you, Chris. Thank you. Just check. Can people see my slides? Just perhaps someone give me a wave.
Yep.
Yeah,
Looks
excellent. Good. Excellent. Thank you very much. Look, thank you very much, Chris, and thank you very much to ESIG for this opportunity to share the Australian experience, and in particular the South Australian experience. And I just noted earlier when I was testing my video this morning that you can see the Anglo-American coal sign in the background. So maybe that's a bit of a reality check of where Australia is in some regards. Okay. So yeah, so firstly, let's jump off into South Australia. There are two aspects which make South Australia sort of worthy of a presentation today. The first one is the physical attributes of the South Australian system. So what Nilesh described Australia and the Australian power system, or the Australian national electricity market, as to the rest of the world, is something very long and stringy and full of renewables. South Australia is to the rest of the national electricity market what Australia is to the rest of the world. So South Australia is exceptionally stringy and exceptionally full of renewable energy. So South Australia has already operated at periods of over 100% penetration of inverter-based resources. Thankfully, it has got a fairly large interconnector to the rest of the power system, so I was able to export those. Power system demand in South Australia cycles as low as about 150 megawatts, all the way up to about 3,100 megawatts. That makes it very challenging to operate over summer. In fact, that 150 megawatt minimum we forecast could potentially fall to zero, or potentially below zero under the right conditions, under a nice balmy autumn or spring Sunday lunch, and that's due to the huge amount of rooftop PV that is installed in the state and continues to be installed in the state. So you can imagine, just from a reserve balancing point of view, it's quite challenging to be able to maintain sufficient economic reserves in the state to balance those requirements. One of the other issues is that South Australia is, even by Australian standards, very dry and relatively flat. That means that there isn't really any opportunity for hydro in the state, or any natural opportunities for hydro in the state, which means that pretty much all the generation there is gas-fired generation. Of course, gas-fired generation has some limitations around frequency rate of change. So yeah, that makes the situation a bit more challenging. And the last thing to note is that the state now has 4 large synchronous condensers, high inertia synchronous condensers commissioned in the state. So that was the first reason that South Australia is worthy of representation, is the physical attributes. The second reason is that South Australia in 2016 experienced a system black event. Effectively, we had a quote unquote 1 in 100 year storm pass through the state. It brought down a number of transmission lines, transmission towers, which put a number of faults into the system. Those multiple faults resulted in a number of wind turbines tripping off, which effectively overloaded the interconnector into into South Australia. And once that overloaded, it tripped, and the resultant was a system black in South Australia. As a result of the investigations into that incident, and some done by Nilesh and his team, and by others in the team prior to that as well, it was found that there was a shortfall of both inertia and system strength in the region. So that ultimately is what led to the introduction of the 4 large synchronous units, 4 large synchronous condensers in the state. So just to go through a bit more of a detailed history. So in 2016, we also had the retirement of the only coal-fired station in South Australia, the Northern Power Station. We had the system black event. Following the system black event, up to the system black event, we didn't have a minimum synchronous unit requirement in South Australia. That was implemented following that event, and some work done by the AEMO team there. Nilesh was part of the team that is then led by Babak, who may be known to many people on the call as well. We declared system strength and inertia gaps. Electronet, the transmission company in South Australia, then had a process to try and close those gaps, and the most efficient way of closing that gap was found to be construction and commissioning of 4 large high inertia synchronous condensers. So that kicked off that process kicked off in 2017. Also in 2017, Elon Musk chipped in on Twitter saying that he could build the world's largest grid connected battery in South Australia and have it delivered in 100 days. And effectively that happened. So the Hornsdale Power Reserve, or also known as the Tesla Big Battery, was constructed in 2017 as well. And that has been a really significant part of the South Australian power system, and a significant reason that we've been able to maintain power system security in South Australia. So following the Tesla Big Battery, we had a number of other batteries installed. The Dalrymple battery in 2018, which is a grid forming battery, although as a relatively small one, only 8 megawatt hours you can see there. Had the Lake Bonnie battery installed as well. In 2020, we had the expansion of the Hornsdale battery, another 50 megawatts and 65 megawatt hours. And then in 2021, we had the commissioning and construction of the 4 high inertia synchronous condensers. So while those synchronous condensers were being constructed, we had a requirement to maintain 4 large synchronous generating units online in South Australia. Since the commissioning of those units, we've reduced that requirement from 4 to 2. And so that's where we are now. So in reducing that requirement, we've had to effectively go through and redefine the South Australian technical envelope. It was a lot of work by a lot of engineers, both in AEMO and Electronet, to do that work. And the result is that we've seen somewhat of a substantial reduction in the requirement to intervene in the market to keep those synchronous units online. You can see there in Q3 and Q4 of 2021, there was a lot of it was very, very hard to maintain those 4 synchronous units online. Since switching to a 2-unit requirement, we've been able to significantly reduce the cost and also the instances of directions in South Australia. As Chris noted, what we need to do is make sure that we maintain critical power system characteristics in the grid. So this is what we do to make sure we maintain a secure power system envelope. And this work that has been going on since the introduction of the 4 large synchronous condensers it roughly also correlates to action 8 that Chris Davies was outlining in his slides to be able to define these technical envelopes and define the operating procedures. So the key areas that we've found for investigation have been around grid formation, management of system separation. We don't want to have another system black in South Australia, so we need to make sure that if we have a unexpected system separation event, that we can at least survive it. Small signal stability and power system damping, ramping and frequency management. So ramping management when that's the ability to withstand the large solar and wind ramps that we have, as noted earlier. South Australia has a very, very high penetration of variable renewable energy, so we need to be able to cater for unexpected large ramps there. We need to maintain a dynamic operating envelope, so that basically means that all our system limits, our voltage collapse limits, our transient stability limits are still going to be relevant for the number of synchronous units that we've got online. A tricky one, one that we've been working quite closely with the network companies, both the distribution and transmission companies, is making sure that there's adequate fault current for protection operation. This is quite a tricky one, requires a fair bit of work by the distribution and transmission companies to calculate what the adequate fault current is at critical parts in the network, and to make sure that the current setup will be able to maintain them. And lastly, control system. So South Australia, due to its nature, its high dependence on a single large AC interconnector, has a number of special control systems in place to make sure that should a system separation event occur, that we can or have a very high probability of surviving it. So the impact on those control systems to effectively work is something that we need to make sure. Again, a lot of work being done here by many teams across AEMO. Nilesh's team is one of the teams that's doing a lot of the heavy work, and I'd encourage you to try and corner him during the breaks to try and get a bit more detailed information out of him. It's really exciting work. It's really challenging work, but it's work that is essential to progressing towards that 100% renewable readiness target. So what are the next steps? So through the work that's been done on assessing the technical envelope, we've been able to, I guess, resolve most of those issues, or find adequate solutions to most of those issues through operating procedures or redefined limits. So probably the biggest and the most challenging part of that work was the grid formation. So that's basically, can we run that power system with synchronous condensers and inverter-based generation alone, noting that almost all of that inverter-based generation is grid following, not grid forming. The only real grid forming battery we have in the system is quite small and is quite energy limited. So that's been a big focus of our work. There's been a lot of work done on that. Again, the heavy lifting done by Nilesh and his team. So please hit him up on that if you are interested. Initial work has shown that it looks like it can be done, and certainly the on paper results indicate that we can maintain grid formation in the state with those synchronous condensers and high inertia and grid following inverters. But we've still got a little more to do there just to make sure. The next big thing is going to be redefining the system limits. So should we actually move to a position where we are ready to reduce the number of synchronous generating units below the two that are required right now? We'll have a lot of work to do with the transmission network service provider, Electronet, to redefine those limits. This will be a huge body of work, but it's one that is going to be required to go to the next step. And lastly, because this is a bit of a world first event, we are looking to do some network tests and network trials. So this again corresponds to what Chris Davies presented in his slides, the action A9 of the engineering framework to do some limited trials on these tests. So look, thank you very much for the presentation and for the opportunity to present. Again, happy for some questions after the slides, and also please take the opportunity for those that are over there in person to have a talk to Nilesh about these issues. So thank you very much, and I'll hand it over to Sam Christie now.
Thanks, James. Can everyone hear me and see the screen that I'm sharing now?
Yep, looks good.
Fantastic. Thanks, James. I'm going to speak a bit about the system strength situation in Australia more broadly. As Chris has mentioned, it is one of the very first things listed in our engineering framework that we need to deal with in the transition. As James has explained, over a number of years, the system strength situation has been significantly improved in the South Australia part of Australia. But we have lots more challenges to deal with system strength across the rest of the national electricity market on the eastern seaboard in Australia. So first of all, I'll give a bit of an outline of where system strength is across the eastern seaboard, and then talk about the regulatory mechanisms that we have in place to try to get that service where it needs to be as we go through this transition. And then finally, I'll talk about the options that are being considered across the area, because there's a number of them in play, and we're hoping that over time, grid forming and advanced inverters will be part of the mixture. The first slide that I'm showing here is to explain the urgent need for more system strength services as we have the transition happen that Nilesh has talked about. So we are having more and more variable renewable energy sources connected largely through entirely through power electronics into the system, as we have significant decommitment or retirement from the synchronous generators across the eastern part of Australia. What that means is that the traditional system strength service that we expect from synchronous generators is no longer expected to be available, particularly as we target this ability to operate with 100% renewable energy penetration by 2025, which we are eager to progress towards. With system strength, I think that the way that we generally summarize it inside AEMO is that it's our way of describing how to keep the voltage waveform stable and in a good shape, both before and after a fault or a disturbance on the system. Sometimes what we do is we refer to fault current injection or contribution as a proxy for system strength. So we measure it in MVA. And we always, though, have to keep in mind that that is just a proxy for us. So, for example, synchronous condensers are there to contribute a fault level injection, but also to keep the voltage waveform stable. And we spend a lot of time trying to distinguish between those two parts of how we explain system strength, because we want to make sure that over time, new solutions, which are not just synchronous condensers, can try to contribute to keeping that voltage waveform stable. So we might refer to fault current a lot for system strength, but it's really not the only way of measuring it from our point of view. And we've spent a lot of time trying to pin down exactly what we mean by this term system strength. What you can see on the screen is for one part of Australia, it's called New South Wales, which is sort of in the centre block of the map. On the left-hand side, you can see our projections over the next 5 years for the number of coal units that we expect to be online over the year. And we've shown in that chart that over time, the number that we expect to be online is reducing. And we've got a black dotted line drawn across at 7, showing that we believe that we need 7 on in that one region, New South Wales, in order to keep the system secure and in order to make sure that there is sufficient system strength for the system. As you can see, we're projecting that we will go below that dotted line in the latter part of the next 5 years. And this is actually a chart that is maybe 3 or 4 or 5 months old. Since this chart was prepared, we have transitioned to a new scenario for how we look at what is the likely situation in Australia over the next 5 to 20 years, which sees a more rapid reduction in the number of coal units online. In addition, as Nilesh mentioned, we have had the announcement of an early retirement for the largest coal unit or coal plant in Australia, which is actually part of this New South Wales region. So this chart, although it shows already a problem in 3, 4, 5 years' time, is actually out of date, and we're going to have a more serious problem, which we're already trying to prepare for and trigger regulatory mechanisms for. What you can see in the map on the right-hand side of the slide is a map showing that, with green being good for system strength, yellow being medium, and red being bad. This is showing where we expect system strength to be a problem by 2031. However, this chart is actually already prepared assuming that the minimum requirements for each of those regions that are shown in the eastern seaboard are already met along the backbone of the system. And this chart actually only shows the system strength issues at the edges of the grid for newly connecting renewable energy. So the assumption here is that we actually quickly move towards meeting the basic underlying system strength requirements that we already have. And then this shows additional system strength needs once we connect even more variable renewable energy. These two charts are in summary showing that we think that part of the very initial part of our transition for the power system is going to need to be dealing with system strength, and then moving on to all the other challenges that that you've seen listed out in Chris's presentation. Because this is such an urgent requirement and such a new way of planning and investing in and delivering services to our power systems, we have made significant regulatory changes in Australia relatively recently. We are currently under a framework that came in 2017 to deal with providing system strength. It's when we started to define the term system strength in our regulatory arrangements. And what we did was we decided that we would need to set a minimum fault level requirement for each of those jurisdictions as a proxy for system strength. So we set a proxy value, a minimum fault level requirement for each region. Then under our regulations, we made an ability for AEMO, the market operator, to decide, according to our projections for what will be online over the next 5 years, where will there not be enough fault level in each region to meet that minimum level. And then we have the ability to declare a shortfall and say, we don't think there's going to be enough there. And then we trigger a regulatory mechanism as AEMO, which means that the local transmission network has the ability to go out and source those services, either from a network asset or from a non-network provider who might be providing some other kind of service to the grid. And in addition, we declare those values for the sort of backbone of the network, and the local network goes and delivers. And then separately, if a new generator connects to the network, they actually need to, under that 2017 framework, they need to bring their own system strength so that they do not make the system strength situation worse on the power system. They provide their own service or they remediate in some way. That's the existing framework. It only came in 2017. However, it's been decided that it's not sufficient. So we now have a even more expansive framework coming in that will apply from December 2022 to deal with system strength services. So under that expanded arrangement, we will be setting, as AEMO, we will be re-looking at those minimum fault level requirements. We will be making sure that they are sturdy for protection schemes to operate, for voltage equipment to operate, and to keep the power system secure. Then we will be also projecting how much new variable renewable energy will be coming into the system. And we will be setting some criteria for how the voltage waveform should be kept stable as that amount of new generation comes through. So we will be setting new system strength standards across the eastern seaboard for Australia. Once we set those standards, and they will be reviewed every year and they will be projected out for a 10-year period, the local transmission network will now have the ability to go out and invest or procure services to meet those standards in full. So we're no longer looking at shortfalls and topping up. We're looking at the network, making sure that every single part of that system strength requirement is met. And as part of either their regulated asset base or as part of services that they procure from providers externally. In addition, the intent of this whole change is to make everything very proactive and forward-looking, to make the services available in general, and no longer, as Chris mentioned, we're not trying to operate down to the absolute minimum. We're trying to make sure that services are ready in advance because the change is happening so quickly. So newly connecting generators will now be able to pay a charge and get in on that centralised service rather than having to remediate themselves. They will also still have the option to remediate themselves, but in general, if they want to, they should be able to buy into that centralised service and make things easier. In order to deliver against that existing framework and also the new framework, we have 3 different sort of modelling realms that we need to work in to plan for those services and to understand the system strength situation in Australia and plan for the services that are needed. First of all, we need to be able to project where there's going to be new variable renewable energy and where there will or won't be synchronous generation, and when it may or may not be on during the day or across the year. So we use Plexos is the product that we use for our market modelling to look at the long-term capacity outlook for generation and for new generator planting in Australia. It also tries to optimise development across generation and network assets and developments, and choose an optimal development pathway. And then finally, we also do significant detailed market modelling, time sequential results, so that we can project when generators may or may not be committed or decommitted across the day and throughout the year. That's one set of projections and modelling that we do. Secondly, we do steady state load flow. So that is, of course, part of the traditional thermal and voltage limit planning for transmission networks. We do that to look holistically at what is happening in the system, look at thermal limits, voltage management. We also pull some fault level projections out of that. And that is based on what we get out of the market modelling, who we think will be online. And then we use load flow to then look at what that might mean for fault level that is available on the system. We try to calculate those long-term projections for fault level, and then we compare them against the minimum values that we've decided would be the minimum amount required for system strength services to be met. However, we are very cognizant that fault level is a proxy only for system strength. It is not nowhere near precise enough to anticipate the needs of the system and the interactions between all the different devices on the system. So a large amount of our analysis for what is needed for system strength and what will keep the system secure is done through electromagnetic transient analysis. So there's a bit of a iterative to and fro between all of these market modelling processes that don't happen sequentially, but with the electromagnetic transient analysis, it's used to assess the power system stability for particular moments in time. We take the inputs from the market modelling about what might be online or available, and then through that electromagnetic transient analysis, we look at what will keep the system stable. We also study inverter interactions and generator performance pre and post contingency. And that process is where the minimum in the first place for the fault level requirement is derived at particular network nodes that are selected as study points so that we can focus the work and the effort, known as system strength nodes. Finally, we also use electromagnetic transient analysis to analyse whether or not the services that are being offered by the transmission network or the non-network providers are actually going to address the need and the problem. I'll move now to talking about what we do once we have a rough sense of what is needed for system strength and we have the regulatory environment in place to get those services. Then we move to the whole implementation situation that James has touched on in detail for South Australia, but is increasingly going to be needed for every single other part of the Australian system, and very soon, really, as you sort of understand from Nilesh and Chris's presentations. I've listed on the slide here the variety of services that we understand may or may not be able to, or can partially or completely meet the system strength requirements on the system as we see the shift away from traditional providers of system strength. So we've got here synchronous condensers, which James has explained in detail how synchronous condensers fitted with flywheels to also get the inertia that helps. For a separate system security issue. So that's one of our options, synchronous condensers. And as Chris has mentioned, it's a known technology and it's something that we're comfortable with broadly. We've also got the potential for hydro plant to operate in synchronous condenser mode. We've actually had 2 instances of agreements in Australia being done where these kinds of plants are engaged to provide that service when required. And it's just a matter of making sure that it's contracted in a way that the service is available when they've got the flows that are needed. We have options for agreements with existing synchronous generators to stay online. That's certainly part of the mix. So if they're not planning to be committed or available, then an agreement with them to stay online and stay available is a definite possibility. We have grid forming inverters coupled with batteries. This is something that is, I wouldn't be able to point to a particular example of that actually having been used yet. I realise that's the topic of the workshop, and we are really eager for that to become something more commonplace and part of the mix. In our view, it's still part of the emerging set of solutions rather than something that is business as usual for us. We've got tuning inverters of existing variable renewable energy. Of course, doing this tuning exercise does not contribute more fault current to the problem. However, it does reduce the poor interactions between devices, which are contributing to the voltage waveform instability in the first place. So that solution can be used to a certain point and not beyond it, so to speak, but it's part of the mix, most certainly, and it has been demonstrated in 2 different locations in Australia from a number of devices. We have temporary constraints on the number of inverters online for existing variable renewable energy. This is another one which is not going to provide the full amount of system strength required, particularly if we're using fault level as a proxy, but it's something that we can do as a measure to reduce the number of issues on the system. It's important that the inverters are actually offline for this to work. It's not just about the renewable energy not providing any megawatts, the inverters need to be offline. Finally, of course, we've got network augmentations. They can help, but the way that they get justified and invested in is a complex process. So, like they need a justification which is quite expansive, of course, and needed for the holistic network operation sort of funding and justification. So those are our variety of services that we believe can help with system strength in Australia at various stages of development. We've got a slide here showing the contribution from synchronous condensers and how they can mitigate post-disturbance oscillations through injection of fault current. So I'll pause to let people have a look. And we've got a link down the bottom to a paper that's been written by Nilesh and others about how the power system can operate with a high share of inverter-based resources. A bit of an explanation of the Australian experience if anyone wants to read further about it. So you can see there the advantage of synchronous condensers. And we also have here a demonstration as well. This is not from the synchronous condenser point of view. This is showing the benefit of the inverter tuning option that I mentioned for existing or new variable renewable energy sources to prevent the waveform distortion in the first place. And that's again, more details in that same IEEE paper. I'm eager to pause soon so that we can do some question and answers with everyone who's spoken today. Before we do that, I'll briefly mention each of the different regions, almost all of them, just so you get a sense for the variety of different system strength needs and services. So on the left, you can see Queensland, which is to the northeast of Australia. This is a site where in the far north at Ross, we've had a solution involving inverter tuning to address a system strength shortfall and problem. And currently in the more southern area at Gingin, the local transmission network is now investigating how to address the system strength shortfall that we've declared at that location. And they've gone to market at the moment to see what services might be available. On the right-hand side is New South Wales, which I was talking about right at the start with the projection for coal units on declining. And again, here, system strength shortfalls have been declared at the major load centres of Newcastle and Sydney West. And this is the region where that major power plant has announced its early retirement. So the local transmission network, again, is now preparing to look at how it will address the problem. Network solutions and non-network solutions are all part of the mix at this stage. At the left here, you can see Tasmania, which is separated from the mainland and is down to the south. This region happily has hydro available. So although they have had system strength shortfalls declared and inertia shortfalls declared for quite some time, they have been able to address them through agreements with existing synchronous generators that are hydro powered, and also some of them have the capability to operate in synchronous condenser mode. And then finally, I won't spend much time on South Australia because James has gone right into the detail there. But of course, on the right there is South Australia, where we've seen the introduction of those 4 synchronous generators, synchronous condensers fitted with flywheels. So I will stop sharing my screen now because I've gone through all the different potential solutions we're hoping to come through for system strength services, which are really urgently needed as part of the initial phase of the transition that we're going through in Australia. Thank you so much, Nilesh.